starting a little bit late. Okay, so the universal statement is something of the form for all x in D, P of x. Now, P of x is the statement you're making, but you're saying it is always true. Now, let's do a really simple example of this. For all x in the real numbers, x squared is greater than or equal to 0. Now, that is a true statement. But the funny thing is, it doesn't have to be true. I could have written something that was false. That's not the point. It's the way I'm saying it. For all x, and here my D is the set of real numbers. This is my P of x. This is my statement involving what I say. Now, if I threw something at you that was not necessarily true, this makes it interesting. So what if I made a grand statement like, that for all x in the real numbers, x is greater than or equal to 9. I'm making a statement. It is either true or it is not. Now, I said for all. That means it has to be true for everything in the domain. And since I said the domain was the set of real numbers, yikes. So what do you do with a statement like this? You can disprove a statement like this. And most of you are familiar with the concept of a counterexample. And I make sure that we understand this. This class is not about counterexamples in general. I don't find that really a good use of time, but understanding that is a valid way of proving something. You see, to prove a true statement is true, you have to prove it's true all the time. To prove a statement is false, you only have to come up with one instance where the statement is false, because otherwise it's not always true. Can you come up with a number that makes this false? Sure. Come up with any number between -3 and 3. And that would prove this statement is false. So let's say that I started the problem by saying D is the following. D is -8, -5, 10, and 100. Let's say that's my D. Now is the statement correct again? Yeah, because if I change this to D, and that's all I'm using, now it is true. So the thing is, a statement is either true or it is not. That's it. If it's not true, you can find a counterexample. I don't want to waste time on a counterexample, but here's one of the things we're going to look at today. If I make a statement it's true or it's not, we're also going to talk about the negation of the statement. That's later on today. And here's the coolest part. If my statement is not true, then the negation has to be true. One of them has to be true. I am here. The negation is I am not here. Well, one of those has to be true because together there's every possibility. So let's move on. That's the universal. Now, what about the other word we learned is the existential. Now, the symbol for the existential qualifier is the backwards capital E, and that means there exists. Now, there exists is sort of the most universally generic way of saying it, but there are other ways of saying it. For example, if I said, well, there exists, let's say, restaurants in my area that are affordable. That's a pretty generic statement. Well, how many restaurants would that be? Anybody want to guess? There exist restaurants in my area that are affordable. How many is that? Can you put a number on it? Anybody? Yell it out.
30.
Wait, there is, well, what if there's only 10? Is my statement still true? There exist restaurants in my area that are affordable. Can anybody put
at least one?
Yeah.
Perfect answer. At least one. That's all I'm only guaranteeing you there's at least one. Now, could it end up being that every single one of them is affordable? Sure. But I'm saying there's at least one. Then there might be 5, there might be 1,000, but that's not relevant. If I said there exists, then I'm guaranteeing existence, but I'm not guaranteeing everything. I'm only guaranteeing one, really. So another way of thinking of there exists, and we don't usually say it that way, but that means there is at least one. It could be more, but but I'm guaranteeing you at least one. So that's what the existential qualifier. It's weak. For all means every one. If there's 1,000 restaurants in my area, for all would be all 1,000. There exists would be at least one, all the way up to 1,000. But I'm not guaranteeing all of them. So we write it the same way. So we'd say there exists an X in D, P of X. Another way a lot of people say this is such that. And we're going to introduce that symbol a little bit later, because when you're actually doing formal statements in logic. So let's say there exists an X in the set of integers such that X is greater than a bazillion. Now, a bazillion is the biggest number I know. It's just huge. You know, it's like one short of infinity. It's so big. At least, you know, that's what I like to say. There exists an X in Z plus such that X is bigger than, well, since Z plus goes to infinity quite literally, can't you always find a bigger number than something? Yes, of course you can. So if you put a value, I got 1,000,000. Okay, well, 1,000,001 is bigger than 1,000,000. So this statement clearly is true, but I'm not saying all X's. I'm saying there's at least one X that's bigger than some fixed amount. That would totally be true. So that's not actually very complicated, that concept, okay? That's a pretty simple thing. Now, let's see. What I want to do is give you a statement, and we want to translate it into some of the vocab part of this. Excuse me. Now, one of the things that we want to get good at is taking symbolic notation and writing it in terms of words, taking words and turning around and writing them into symbolic notations. All right. I'm going to give you one right now. Okay, this actually is a true statement, and it's a simple statement. This is, right off the bat, I'm throwing you into the deep end. Well, we want to be able to clearly translate, because like I said at the beginning, I want to be able to take a mathematical statement, translate it into words. I want to know that every possible way of saying it is true. So then I can say, what's the contrapositive of that, which would also be true? What's converse, inverse, all that? What's the negation of that statement? Both symbolically and in words. I want to be able to do that with anything, because if I can do that, then I'm much more fluent in my translation. Now, that's the element symbol. Q plus would be the set of positive rational numbers. Remember, a rational number is any number that can be represented as a quotient of integers, 2/3. Well, what about the number 5? Is that a rational number? Yeah, because that could be represented as 5/1. An equivalent representation. Oh, okay. So all integers are rational. Not all rational numbers are integers. And any integer can serve as the denominator except 0, because then the number would be undefined. That's why I said Q plus. So this says for all X element of Q plus, there exists a Y in Q plus such that X times Y equals 1. So what I'd like you to do is, let's just take a moment. I would like to know, can somebody translate that into simple English? This is not trivial, but this is really important in the big picture. Can you translate this into English? So what we want to do is we want to avoid using qualifiers if possible. You see, if I translate, I'll have some fun with you. I did this last semester, and I'd have people say, okay, I'll translate this for, and you can't use any variables or anything. You can't use anything. So they'd say for all X. See, because I can't use variables, so I'm going to spell the word X. No, that's not what I mean. Don't spell all of these. That's kind of silly. Okay, I'll give you a hint how to start it. For every rational number. That's the first thing I'm going to write. For all X in the set of, or I'm sorry, for every positive for every positive rational number, or
There-
simply every positive rational number,
there is another positive rational number such that the product of those two numbers is 1.
all right? Now, that is absolutely correct. Can we say it in such a way that's even less mathy? That's a word, by the way. Everything you said is correct. Every positive rational number for x times y to equal 1, what must be true about y? What is y is defined to be automatically if x times y equals 1?
Positive rational number?
Say again?
Positive rational number?
There's a word I'm looking for. It's another R word.
Is it called a reciprocal?
Reciprocal. So every positive rational number has a positive reciprocal. That would be one translation of this. By the way, is that the only translation? No, someone said every positive rational number, there's another number such that when I multiply them out, I get 1. That's an absolutely correct statement. And that was a statement, that was sentences. That was not all math symbolic. But an easier way of saying it is every positive rational number has a positive reciprocal. Ooh. Now, why can't we say every rational number has a reciprocal? Why can't we say that exactly? Because there's one rational number that doesn't have a reciprocal. What is it?
0.
0. Yeah, that's okay. So that's why I said positive. But the point being, the translation is huge. And we wanted to, for all x in rational numbers, I'm translating in English, for all x in the positive rational numbers, there exists a y in the positive rational numbers such that x times y equals 1. All I'm doing is translating each symbol into the exact word. That's sort of missing the spirit of it. This is symbolically, if you were speaking to someone, oh, okay, how would I say it? So I took something really complicated, but that's the idea of the translation part of it. Okay, so now let's do one in reverse. Well, I'm going to give you a sentence and I want you to translate it into words. Ooh, okay, so we'll keep it simple. There are real numbers that are larger than their, how about square roots? There are real numbers that are larger than their square, oh, I can't spell, than their square roots. That would be an EIR. Now, first of all, do you even believe that statement? There are real numbers that are larger than their square roots. We'll take any number bigger than 1, right? That's going to be bigger than its square root. So yeah, I believe that statement is true, that there are real numbers. By the way, if I took a number between 0 and 1, what do you think? If I take a number between 0 and 1, then it's smaller than its square root. But I'm not saying this is always true. I'm saying there are situations where it's true. Therefore, if I'm going to translate this into mathematical symbols, everybody take just a moment. Let's see if we can translate this into mathematical symbols. I'm not going to call you on it, but let's see if we can do it on our own just for a second. First of all, am I going to be using the universal qualifier or the existential qualifier in this? Anybody want to try that one?
Existential.
I'm using the existential because I'm not saying it's always true, but I'm saying there are instances. And by the way, more than one instance, but I can think of at least one number that's bigger than its square root, 9. Okay, that's all I needed. I just said there are, I didn't say every. The problem with every, because then I can come up with a counterexample. So how about there exists. So what is the translation of this? There is a real number. There is a real number such that, by the way, you can use the word such that. The backwards element symbol is the word such that. That's a mathematical symbolic notation. This is a universal thing. That is element. X is an element of the real numbers, means X is a real number such that, so there is a real number such that what? I said it's larger than its square root, such that X is greater than square root of X. That's it. So that wasn't so bad. Being able to translate is actually quite useful. Okay, now is that the only way of saying it? Well, not necessarily. Okay, now here's, I'm going to give you a little exercise. And I would like to know, are there, if I started with this, are there other ways you could say this? In other words, rearrange the words. Can you rearrange the words and say the same thing? This is a simple exercise because in math, we can run into trouble. Remember, when you rearrange the words, you could be taking a conditional statement and unintentionally writing it as its converse. So rearranging words is a little bit dicey sometimes. Can I rearrange the words? Let's say we started with this statement here. Well, many of us would have translated it into something like this. But is this the only translation is what I'm saying? For example, I'm saying, well, there are numbers out there that are bigger than their square root. That's kind of what I just said. There are numbers that are bigger than their square root. Well, that's not exactly the same wording as that, but it certainly means the same thing. How about a number is bigger than its square root for some real numbers? That's another way of saying the same thing. Again, I'm rearranging the words to give the same intent. So that's a simple exercise when given this. So if we'd started with this statement here, and I ask you to translate, not everybody in the room is coming up with the exact same thing word for word, but we hopefully would all be coming up with the same thing in terms of overall concept, that what we're saying is actually a translation of this, but we don't want to leave it open to other things. Excuse me. Okay, so with that, let's see. I want to do a couple of simple examples. Let me write it. I'm gonna steal one from the textbook, and I'm gonna ask you guys. You don't need to write it down. I'll tell you which problem I'm doing, but you don't really need to write it down. You just need to listen. Let me write down the. What did I just do? Oh, pens. Here we go. It's just dark enough here that I'm sweating. Okay, there's this ordinal such that x squared equals 2. Okay, here's a statement. It is either true or it is false, but we're not measuring the truth of this statement. Okay. In fact, the fact that you could solve it means yes, it is true. I said there exists. I didn't say every x in the set of real numbers. Now, I'm going to read you some sentences, and I want you to tell me, and again, you can just blurt it out if you want, if it's the same thing. Okay. The square root of each real number is 2. Is that, in other words, is that a translation of this? What do you think? True or false?
No, it's not a translation.
No. Good. Okay. Next statement. Some real numbers have a square of 2.
That's true.
Yeah. Some real numbers. In fact, you can think of exactly 2, can't you? Root 2 and the negative of root 2. Okay, good. The number x has a square of 2 for some real number x.
Yeah.
That's kind of a long-winded way of saying it, but here's the whole point. I'm giving you a mathematical statement, and 3 different people might have come up with 3 different translations. We just want to know, is it still saying the same thing? All right. If x is a real number, then x squared equals 2.
No, that's not true.
No, did I just basically use a universal qualifier there? I did not say for all. I said if X is a real number. Isn't that
It's
the
the
same
same thing in this context, I think.
Yeah, I said if X is a real number, isn't that equivalent to saying then
It is.
all real numbers? Yeah, because X is a real number, therefore I'm saying it must always be true. So that would be a bad one. How about some real number has a square of 2? I haven't used that one yet, believe it or not. Some real number has a square of 2. True or false?
I'd say
Translation.
true.
Yep. And last one. There is at least one real number whose square is 2. There's at least one real number whose square is 2. True or false?
True.
True, because we agreed that there exists is also equivalent to saying there's at least one. Now, I just read you 6 different statements, and I think we came up with 4 of them were true statements. In other words, 4 of them were correct translation of this, but they were all different. That is the point. But I also gave you a couple that were not true. So the danger sometimes when we're translating is we could actually say something that's not true. And well, obviously that would be very, very bad. So that's actually a pretty simple exercise. So now I want to move on to some of the meatier stuff, because this is where it gets really cool. We're going to start talking about negations now. Okay, so a universal statement, we said before, is anything of the form for all X in D, P of X. And then P of X would be the statement that I'm claiming is either true or false. Okay? For all X in D, P of X. For all real numbers, okay, that's a statement. Whether it's true or false isn't the point. That's a statement. I'd like the negation of that. Ooh, the negation. So this is what we want to get to. How do you make the negation of a statement? Well, we said, well, we're just throwing the word not. Yeah, but where do you throw in the word not? You see, you got to be careful. If I said, you know, the statement P of X, that's my statement. Well, not P of X, then is my negation. You're absolutely correct. But there's more going on in here. See, I've also got the qualifier. Ooh. Well, I'm saying in English, the square of every real number is positive. That's a simple English translation. The square of every real number is positive. With those words, what would the negation? The square of every real number is negative? Would that be the negation?
I think it would be there exists a number whose square isn't positive.
Good. You see, I want to remind you that by the way, beautiful. The negation of my container is full. The negation isn't my container is empty. The negation is my container is not full. Empty is included in the not full. So we don't say every single situation. So I'm saying the square of every real number is positive, and you're saying the negation is that statement would not be true. There's got to be something out there where that's not the case. There's got to be something out there where the square isn't positive. We're not saying the square of every number is positive. No. We're saying there's going to be at least one case where that's not true. Remember we talked about proving something with a counterexample? If to come up with a counterexample means you came up with one instance where the statement was not true. For a statement not to be true, you don't have to prove it's false for all occurrences. You only have to prove it's false for one occurrence. So in this case, can I find one situation where this statement is not true? So the negation of this statement beautifully is there exists an X in the real number. There exists an X real number such that what? X squared is, now what would the negation of X squared greater than 0 be? Technically, in the strictest sense. What's the negation of this? We just did this on the quiz you turned in, actually.
Less than.
Less than or
Less than, careful, or
equal to.
equal to.
or equal, yeah. Got or equal. Think number line. By the way, I'm having people, and I made a point of this. So I said the negation of this would be no. You negation of an inequality is an inequality. That is an incorrect way of saying anything, because this is totally ambiguous. No, the negation of an inequality is an inequality because an inequality is binary. It's the other direction. That's the negation, because it's the complement. Careful. You don't say then what's the negation of on? Not on. No, off. Because not on is off. You don't say not on. 1, 0. What's the negation of 1? Not 1. No, it's 0. Yeah. When there's only two choices, you put the other choice. It's a negation absolutely all the time. So there exists in our. So this, how do we say it in this way? By the way, what you guys are saying is beautiful. So here's the universal statement. So here's what I want. How do I say that? Now, you just gave me a beautiful example. So if nothing else, if you don't get anything out of today, the negation of a for all cannot be another for all. In other words, the negation of a universal statement cannot be another universal statement, because now you're talking antonyms. See, now you're saying the negation of full is empty. No, that's the antonym of full. That's a word that has the extreme opposite meaning, but there's an infinite number of cases in between. So that's where you gotta be a little bit careful. So the negation of for all, which formulas like this, is there exists an X in D. There's at least one case, and I'm going to put such that not my conclusion. So in this case here, there was at least one real number such that that was not my conclusion, right? Less than or equal to 0. So the way you guys stated was beautiful. That was perfect. I didn't even give you a heads up. You just did it. So this is the universal statement. Here's how I formally say it. Now I want the negation of that universal statement, and this is what we get. And so here's where we put the 3 bars, meaning it's equivalent to, in this case here. Equivalence is huge. Like when you're doing a truth table, equivalence means this statement here has the equivalent meaning of that statement there. But this statement here is a little easier to digest. Now that's the universal. Okay. What if I said there exists X in D? And in this case, we say such that P of X. There's no such that here. For every possible situation, this statement. There is a situation such that this statement. This you have a such that always with an existential. I just want to point that out. That's always going to be the case. Now, there is an X in D such that this is true. Okay, let's do a simple statement. There exists an X in the set of rational numbers such that X squared is greater than 2. Of course you believe that. Just take a really big rational number, positive or negative. There exists an X in the set of rational numbers such that this is a true statement. Okay. Let's start with this one. What would the negation of that be? There's an X such that that's true. Wouldn't the negation be something like there isn't? I mean, let's just start with logically. When I say something, at least once I flew over the world by myself, and you said, no, that didn't happen. That'd be the negation. No, it didn't happen. Okay, so I think we all agree that, no, this ain't true. This ain't happening. But now how do I say it mathematically? There isn't an X in Q, but there isn't. There's at least one occurrence where this is true. The negation would be, and when we try it in words, there's at least one occurrence where something is true. The negation would be,
there are no occurrences.
there are no occurrences where it's true, or for all occurrences,
they're not greater than 2.
No, keep it. There's at least one occurrence where something is true. You're saying there's no occurrences where it's true. So that would be equivalent to saying for all occurrences, it is false. Do you agree with that? there's at least one time something is true, the negation would be, there's never a time when it's true. That would be equivalent to saying it's always false. So since we can't really say there's not, we'll say the negation would be, how about for all x in Q, not this. How do you say not this? X squared. Does that make sense? So the negation of a there exists means there isn't, which would mean it's always not the case of my conclusion. So I don't negate the there exists. You don't negate the for all. No, the negation comes with the conclusion. That's also called the predicate, by the way. Just, that's a vocab word. I'm not really worried about that one. So in general, I'll write it up here. I'm running out of room here. So my original statement was, there exists an X in D such that some conclusion. I now want the negation of there exists an X in D such that conclusion. Well, simple English would say, well, there's not going to be an X in D. That's true. But I don't really have a way of saying there isn't anything. Instead, we'll say it is always the case that this will not happen. So to say something will never happen, that thing will not happen. For all X in D, not P of X. That's it. So the negation of a universal statement involves an existential statement. And now we see the negation of an existential involves a universal. That's really important that we see that distinction. But notice that, again, the conclusion is the not. Okay, so it doesn't matter what I said mathematically. It doesn't matter if what I say is true. The negation I can always claim. So I could say something completely absurd. And then if I say, what's the negation of that? We want to be able to correctly navigate. Because if you were reading something mathematical and you say, and it made some claim, you go, I don't believe that's true. I've come up with a counterexample. Great. You prove that statement is false. But if another situation you're saying, this says the following is always going to occur. I wonder what the negation of that would be. In other words, can I approach this from another direction? Yeah, to be able to negate a statement is actually kind of a powerful tool. So negating a universal, negating an existential, big picture. Okay, let's keep going. Let me do an example then. Oh, let's go back to the one we did earlier. Sorry. All right. So earlier, all right. I would like the negation of this symbolically and in English. Oh boy. Well, you already translated the English for me. So whether you negate it in English first or symbolically first, it really doesn't matter. But I want you to be able to do both. So the translation was, okay, every positive rational number has a positive reciprocal. That was one translation. Remember, there's always multiple. Another correct translation was every positive rational number, okay, for every part, there is another positive rational number such that the product is 1. That's another way of saying the same thing. So the negation has to be not a for all, it has to be there exists. So everyone on your own, let's try this for a moment and see if we can make this make sense. Well, I think we all agree that the negation of this negation is going to be a there exists. There exists an X in Q. There is an X in Q out there.
For all Y.
There is an X in Q such that for all Y in Q plus, we don't want to change our domain. Now, drum roll, please. Conclusion. There's no
So I
start
not equal 1,
X, Y.
not equal 1.
Beautiful. That's it. That's perfect. For every situation, we meet this. There's at least one situation where this is not the case. Now, remember, the negation doesn't, you don't negate for all. Like I said before, you negate the conclusion, the predicate. That's the part that you're actually negating. The negation of for all involves that there exists. So again, the negation of for all x p, there exists an x such that not p. That's what we just did. This is beautiful. So now let's translate this into words. Remember, my original statement was true. So in this case, the negation would be false, but that's irrelevant. Don't get bent and call, well, you know, I don't want to say it because it's not true. No. This is just practice. Remember, I talked about when I used to introduce logic and when I taught high school, I would use gibberish. I would use the Jabberwock. It's not relevant whether something's true or not. It's, I want to know, how can I say something with the equivalent meaning? It doesn't matter if it's true. I just want to know, am I translating it? So this statement is true, so the negation can't be true. But what am I saying here in words? In words, there is a positive rational number. I used the word reciprocal when I translate it because I'm lazy. It was easier to say it fast, but I think you really do want to use the reciprocal this time. There is a positive rational number. Anybody want to finish this statement for me?
That doesn't have a reciprocal?
It doesn't have a reciprocal. Beautiful. You guys are on today. That long weekend really helped, I guess. Now, we know that's not true. That's not important, but that's what we just said. You could also say there is a positive rational number that doesn't have another number where when I multiply them out, I get the number 1. I don't like that. That's too long. I got lost somewhere in the middle of that sentence. I forgot what I was trying to say. So yes, I could say something about the product being 1, but it's too much there. Not having a reciprocal, because remember the definition of a reciprocal, people sometimes forget the definition of reciprocal is, oh, it isn't 1 over a, the reciprocal of a. No, the definition of reciprocal is a number such that the product equals 1. The 1 over a is what you get if you solved the problem. The definition of a reciprocal of a number is when you multiply them together, you get 1. That's the definition, not the 1 over part. No. Because otherwise, when you have fractions or you have roots or irrational numbers, it would be really muddled because there's so many representations of the 1 over part. So if I just said, no, what's the reciprocal of a? 1 over a, because a times 1 over a equals 1. That's the reason. And so that's beautiful. You guys came up with that one. All right. Now, I'm going to give you just some really simple algebraic statements. And I want to come up with negations. That's kind of our big theme today, is coming up with negations of simple statements. Okay. Let's start with one. For all x in Z plus, if x is less than 1, then x squared is less than, whoops, I'm sorry, if x, not less than 1, sorry. Can't really be less than 1 if I'm in the positive integers. I'm sorry. If x is greater than 1, then x squared is greater than 1. All right. I'd like a negation of that. And by the way, that statement is true, but that's not important. So in English, this says for every positive integer, or every positive integer greater than 1, its square is greater than 1. We'd say, yeah, I believe that. So now think about this for a moment. I'd like you guys to help me out here. What do you think the negation would be? I'll write it down.
There exists x of integers
And again, I can't change the set where something came from, because then that would, okay, there exists an X. Now I put such that, remember on the there exists, we always have the such that what?
If X is less or equals 1.
Ooh, careful now. Oh boy, this is, ooh, I got you on this one. The negation would be, am I negating this or am I negating this? Ooh, careful. Now, this is not an easy one. How about if X is greater than 1, then X squared, what's the negation of this?
Less or equals.
Oh, so I'm just saying, hey, there's one out there. There is a positive integer greater than 1 whose square is less than or equal to 1. Does that make sense? Or you could say it such that X is greater than 1, and this might actually be a better way of saying it, because that's technically a better negation. Both of these would work, but I'm not negating this part. I'm negating the final thing I'm saying. You see, because if I said, well, X less than or equal to 1, then, well, but if X is less than or equal to 1, X squared being less than or equal to 1 wouldn't really be false anymore. Remember, because it's coming from positive numbers. So you go, wait a minute, no, I need the statement to mean something completely different. This one was a little bit tricky. I didn't say it was easy. We're going to work with negations on conditional statements in a moment. All right, let's do another one. Now that seems like a weird statement. By the way, is that a true statement? Now this is a tricky one. Can you ever prove something is true by example? You've always been told you can never prove something is true by example. You can only prove something is false by example. Actually, that's not true. If I make a universal statement, you can prove it's false with an example, but you cannot prove it's true with an example, because remember, for a true statement to be true all the time, you have to come up with all the occurrences. But that's a for all. If I say there exists, all you got to do is come up with one case where it's true, and then I've proved there exists a case where it's true. That kind of flies in the face of what we've always said. No, true statements have to always be true. Yeah, but I didn't say 3x is less than x for all real numbers. No, I said there's a real number out there where that's true. And if I can find one real number where that's true, then that statement actually is true. I'll give you a hint. Think of any negative number. Oh, yeah. This is true for every negative number, in fact, isn't it? You think about further down the number line. So actually, it's not important whether the statement was true or not, but it is kind of nice to know ahead of time. Yeah, this is a true statement, but I want the negation. So the negation of this statement would be, well, we know it's going to involve a for all, but the tricky thing is, I want it not to be the case. So I'm saying there is a real number where 3 times the real number is smaller than the number itself. The negation is there isn't a real number where that's true. But I can't start with there isn't a real number where it's true. So I have to start with, okay, it's never true. So for all real numbers, it's not true. That's the same thing. Something never being true is for all instances, it's not true. Otherwise, you say there's nothing at the beginning. That's so now I would say for all x in R, what? There's no such that comes in. Ooh. Make sure you're muted. That was kind of ear piercing. For all x in R, now I'm going to make a statement, but my statement's now going to be the negation of the predicate here. So for all x in R, anybody? Remember, what was the negation of an existential? You can just remind the negation of there exists X in D such that P of X, remember the negation is for all X in D, not P of X. That's the negation always. So what is this going to be? For all X in R. Anybody want to try it? What do you guys think? On top of things.
3x larger than equal x,
3X,
larger or equal x.
yes. Absolutely. Perfect. That's it. Because that's the negation of my predicate again. So you guys, you kind of get the feel that this is kind of a game. It's really not that complicated to negate a statement that's a for all or there exists. It's a form. When it's of a form, you do the following. I personally like using, simple algebraic statements because sometimes that just makes it easier. But what if I said it in a sentence form? Ooh. Every time I go to the store, I pick up a carton of milk. That's my statement. Every time I go to the store, I pick up a carton of milk. What's the negation? And I want English. I don't want symbolic because that's too confusing. I gave on the last quiz, I gave just a simple statement. I think it was Isaiah is a martial artist and a math stud. And I said, what's the negation? And I feel like, not P or not Q implies what? There's no P. There was just a sentence. There's no P's and Q's. It was a sentence. I don't need to translate it to symbols. Every time I go to the store, I pick up a carton of milk. What's the negation?
There exists a time I went to the store and did not pick up a carton of milk.
Okay. Would you actually say there exists?
I would.
How about, I like it. How about there are times I go to the store? When you're talking to your mom later on, Mom, there existed a time in my life when I went, you probably wouldn't have said it that way, but you're right. There are times I go to the store, or there's at least one time. How about there's at least one time I went to the store and I didn't pick up a carton of milk. You don't say I never go to the store because that would be incorrect because I said every time. So I gave you a universal qualifier. A lot of times there are universal or existential qualifiers in a statement, but we didn't exactly use the words for all or there exists. You have to be aware, okay? If X is a real number, then that's a universal qualifier. If X is a real number, then I'm going to say something about X. Aren't I saying for all X's in the real numbers, that thing? Yeah. Oh, so sometimes it can be one of these without using the exact same words because the implication is there. That's really important that we recognize that translation. And when we're doing the English, that's kind of cool. All right. So now let's have some fun in terms of translating. All right. I always like this one. You're going to like the next quiz. It's one of my favorite series of questions. I'll give you a hint. On the next quiz, we're going to be working with conditionals, contrapositives, inverses, converses, negations of everybody's the most important of all, Luke, I am your father, join the dark side. That's the statement I'm giving you, and you're going to pick it apart and analyze it. So I'm going to come up with a more simple statement. I am going to the store to buy tots. Tater tots, yeah. I am going to the store to buy tots. All right. That is not a conditional statement. That is not anything. It's just a sentence. What I'd like is the conditional, the converse, the inverse, the contrapositive, and the negation. And I would like everybody to do this on their own. I'm going to give you a couple minutes, so I'm going to stop recording. One of the things people always have trouble with on one like this is it present tense, future tense, past tense? That's not really life and death, but I am going to the store. It hasn't happened yet. So don't say I went to the store. That probably is the only thing that doesn't make sense. So if I go to the store, then I will buy tots. So if what you said essentially is the same as that, if I am going to the store, that's the same thing. If I go to the store, then I will buy tots. How do you say the converse? Anyone want to try that one?
If I buy tots, then I went to the store.
One's future, one's maybe change the tense. If I bought tots, then I went to the store. Or if I'm going to buy tots, then I'm going to the store. Does that make sense? If I'm going to do it in the future, then I went to the store in the past, probably. So if I buy tots, then I am going to the store. The only thing is, I'm a math guy. I'm not an English guy, but I really shouldn't have a sentence that has future and past at the same time. You know, I'm going to do this thing in the future that I did in the past, or I'm going to do this thing in the past that I'm going to. Yeah, if I buy tots, I'm going to the store. Now, the inverse. Ooh, which one's the inverse? P implies Q. The converse, Q implies P. Which one's the inverse? Anybody? That's the formal. What's the inverse of these?
Not P, not Q.
Not P implies not Q. By the way, this is probably the one that's used the least. It's probably the most obscure, but I still want to know it. So if I do not, or I don't go to the store, then I will not buy tots. Do you all agree with that one? Now, which one's the converse? P implies Q, Q implies P, not P implies Q, or what's left? Not Q implies not P. If I, now again, you can do future or past. If I didn't buy tots, then I didn't go to the store. That's okay. If I do not buy tots, then I will not go to the store. Again, or if I didn't buy tots, then I didn't go to the store. You're saying the same thing. Now the negation. Oh, this is the trickiest one. What's the negation? I'll give you a hint. The negation is not an implication. Remember, think of the negation as if the conditional statement is true, then the negation would be a lie. I like to think of it like that. I know that sounds terrible. Remember, the negation, the conditional statement is if hypothesis, then conclusion. If hypothesis occurs, the conclusion is guaranteed. I'm making a promise. If you do your part, then I will do mine, I promise. What's the only lie? You did your part, but I didn't do mine. That's not an implication. It's P and not Q. The hypothesis occurred and the conclusion didn't occur. By the way, that's the same as saying but the conclusion. In that context, but does mean and. So I go to the store. I went to the store. I am going to the store. However you say it. I go to the store and I do not buy tots. Again, the tense, present, past, future is less critical. Just be consistent in the sense. You don't say again, I went to the store, but I will not buy tots. Well, that doesn't work. I already went to the store, but not buying them in the future. So I went to the store and I didn't buy tots. I am going to go to the store and I'm not going to buy tots. Any version of that is the same thing. So the ability to take a sentence and pick it apart is critical because remember, the conditional and the contrapositive are saying the exact same things. So when we do things, by the way, with necessary and sufficient conditions, it's kind of the same thing. I'm going to leave some of those for you to read because it actually is pretty simple. And you're going to find the practice problems in the text are really simple to navigate through, but you want to go through a lot of them because there's so many versions and variations of the types of questions that you're going to be able to do and that you're going to want to practice. All right. So I will stop there. This is how